Hey, let's talk about RSA. And we'll start with the textbook version of RSA, which is the thing that I guess you learn in school here. So this is like the naive version to do encryption. You just raise your message to the power of the public exponent E, do all this modulo n, and then you get some ciphertext, and well, that's it. So what's the problem with this scheme? So yeah, there are several problems. One is that if I encrypt 0, the ciphertext will just be 0, and if I encrypt 1, the ciphertext will also just be 1, which is kind of obvious. And more generally, this encryption algorithm doesn't use any randomness. So this whole encryption scheme doesn't have any chance of being like CPA secure or anything, which is like the minimum security level we want for public key encryption. So yeah, this is not good. However, the thing that RSA is actually good for is that this map here is a trapdoor permutation. That's the RSA thing. That's what it's good for. And so in the lecture, we basically said, okay, we don't encrypt it like this. This is stupid. We instead encrypt it in two parts. We choose a random x, and we raise that to the power of e, which is already much better because one-way permutations are only good for something if you give it random input. So we give it random input, random x, and then we use the hardcore bit of x in order to encrypt the message. Then if I want to decrypt, I can raise x to the e to the power of d, then I get x, and then I get the hardcore predicate of x, and then I can XOR that with this part and get my message. Yeah, so two things. This hardcore predicate here, for RSA, we can just use the least significant bit of x as a hardcore predicate for x. And then we've proven this whole thing secure, not for RSA directly, but generically. I want to talk to you about a different construction for this. My proposal is as follows. I take some hash function h, and then I use that hash value to blind my message m with. Okay, decryption still works in the same idea. From x to the e, I can recompute x, and then I can compute h of x and get my message through that. And I also claim that this is secure. At least it's secure if this hash function here, if we model that as a random oracle. So, question for you, how does this proof go? As usual, we assume we have an adversary A against this RSA encryption scheme with the random oracle, and we construct an adversary A prime against the trapdoor permutation. So what's happening anyway? From our challenger, so this is the trapdoor permutation challenger, it will give us parameters for the trapdoor, which I'll call pk here for simplicity, and it will give us some y. And our goal is to invert y. So how do we do this? We give the public key to A. A will ask oracle queries for h of x. And our trick will be that we will just hope that at some point A will query for the hash value of our preimage that we're looking for. And if it does that, then we just output x to our challenger and we'll have won our RSA experiment. A also outputs two messages. And we need to generate an encryption for it. So what encryption do we generate for the challenge ciphertext for A? Yes, so we use the y from our challenger because that's what we're hoping the adversary will try to invert then, right? And we just put some random value into the second component. Just choose it uniformly at random. And well, at the end, A outputs a bit, but we don't actually care about this bit. Our hope is that at some point this will happen. that the adversary queries our pre-image. Now let's look at two cases. In the case where this happens, so where A at some point queries X such that X is the pre-image of Y, then we'll have 1 and then that's fine. So we don't care what actually happens to A then. In these cases, everything's perfect. The other case is that this never happens. So the adversary never queries h of X for the pre-image of Y. But in that case, notice that our ciphertext here would be like a good simulation of what A would actually see in the normal RSA encryption experiment. Because in the normal game, this R would be h of X, X or MB. And if A never queries h of X, this h of X, X or MB will just be like independent of B. It will just look perfectly uniformly random, independent of everything else, because kind of this random oracle hash value has not been fixed in any way. And so the chances for A to win, to output the correct bit, in that case, if he never queries h of X, is just 1/2, exactly. So we can summarize this as in this scheme, exactly the only way for A to gain any advantage in learning about MB is to actually query the hash function for X. But to query the hash function for X, you need to actually invert Y, which according to the RSA assumption should be hard. So you can do the formal analysis, which will boil down to this case distinction whether or not A queries the hash function. If A doesn't query the hash function, its advantage is 0. So these cases kind of, and because we want to prove that A has a low advantage, these are like the good cases. And if A does query the hash function at this position, then he may just win with probability 1. But also in this case, our reduction would show that in this case, he has inverted the RSA trapdoor permutation. And this is hard to do. And this would allow us to construct this adversary against the RSA trapdoor permutation. All right, that was it for RSA encryption. Similar to RSA signatures, again, it turns out that like for deterministic stuff, like for deterministic messages for the signature scheme and for deterministic messages in the encryption scheme, RSA is just horrible. But if we only feed RSA with random values, and in the case of RSA encryption also do some random oracle stuff or hardcore bit stuff in order to get actual indistinguishability from somewhere, then this whole RSA business kind of works out. So thanks for watching this brief look at how to do RSA encryption, and see you.